Good day. In this video, I will going to discuss lesson 5 for module 2. This is all about systems of equations. By the end of this lesson, you will be able to understand the theory of systems of equations and solve systems of equations using these three methods. These are the method of substitution, elimination, and Cramer's rule. Now, before we proceed to the different techniques in solving systems of equations, we will know first the theory behind these equations. Now, many problems in science, business, and engineering involve two or more equations in two or more variables. We relate two or more variables, we relate two or more parameters. So to solve such problems which involves these parameters or variables, so we need to find solutions of a system of equations. Here is an example of a system of two equations. We have 2x plus y is equals to 5. This is our equation 1. And 3x minus 2y is equals to 4. This is our equation 2. We have two equations here that relates the two variables or two parameters x and y. Our goal here is to solve for the value or values of x and y that will satisfy these two equations or either of these two equations. Now, the other term for the values of x and y that satisfies either of these two equations is known as the solution of the system of equations. And the solution of the system of equation is represented by an ordered pair. For two equations, two unknowns, we have um, open parenthesis x comma y, then close parenthesis. If we have three equations with three unknowns, the format of our ordered pair will be x, y, and z. Now, these values should satisfy each equation in the given system in order for it to be included as the solution of the given system of equations. Now, let's proceed to the different methods or techniques in finding the solution of a system of equations. We have the method of substitution, elimination, and Cramer's rule. Now, each of these method has advantages and it also has limitations. Now let's explore each of these methods. Now, for method of substitution, it will work best for linear or nonlinear system of equations. And then you can only use this one for two variables. Although although there are some cases that you can still use this for three or more variables, but it would be lengthy if you use this one. So the ideal type of system for method of substitution is either linear or nonlinear in two variables. Now, the second method, which is the method of elimination, will work best for linear only, because for nonlinear, you find it hard to eliminate those terms that have different exponents or different expression in it. So for elimination, this works for linear with same variable and corresponding exponent, and then valid up to two variables only, because if we have three or more variables, it will be a lengthy process. Same with the method of substitution. But still, you can use this. But the um, disadvantage of that is um, you will have a very long solution. Now the third one, Cramer's rule. This method uses the concepts from matrices, specifically the determinant, in finding the solution. And for Cramer's rule, it will work for linear and then two or more variables with corresponding two or more equations. For Cramer's rule, it is only limited to equal number of equations to equal number of variables or unknowns. In other words, you cannot use this if you have an equal number of variables to the number of equations. Now let's start with the method of substitution. From the word itself, substitution, we are going to express the given variable, or we're going to express one variable in terms of the other. And then after that, we're going to substitute that expression of a given variable to the other equation in order to solve for the other variable. Now, this is the procedure in performing this method. So first, as what I have told you, you're going to express one variable in terms of the other. Say for example, you are going to choose x. So you're going to solve for x in terms of y using one of the equations, one of the given equations. After that, you're going to substitute that expression from step 1 into the other equation to obtain an equation that only contains one variable. So what I am referring here is method of substitution for two equations with two unknowns. These are x and y. Now once you substitute the expression, you will end up with an equation that only contains one variable. And you can solve the unknown variable. Now the third one is solve the equation obtained in step 2. And then once you obtain the value of the other variable, now use that one in order to solve for the variable from step number 1. So the method for that is back substitution. So in step 4, back substitute the value obtained in step 3 into the expression obtained in step 1 to find the value of the other variable. And lastly, make sure to check those values for x and y if it satisfies each of the original equations, because there are some cases that it will not satisfy the equation. If it will not satisfy, then um, those values are not part of the solution of the system of equation. Now let's have an example for this one. So determine the solution of the system of linear equation below. Now we have a two equations with two unknowns, x and y. So this will be my equation 1 and this will be my equation 2. Now the type of equation that we have here is a linear equation because the degree for both x and y is 1. Now for method of substitution, you have the freedom to select which of these two equations uh, you are going to modify. That is expressing one variable in terms of the other. You can select equation 2 or equation 1. In my solution, I will select equation 1. So in equation equation 1, I will going to express x as a function of y, or x in terms of y. So I have 1/2 x plus 3/4 y is equal to 10. In order to avoid fractions, I will going to multiply both sides by the LCD of 2 and 4, so that's 4. So 4 times 1/2, that will give me 2x, then plus 4 times 3/4, that's 3. Y is equals to 4 times 10 is 40. Now I will going to transpose 3y to the right side, leaving 2x on the left side. So 2x equals to 40 minus 3y. Divide both sides by 2. So I have x is equal to 40 minus 3y all over 2. So this will be my x in terms of y. Now I will going to use this to equation 2 so that I can arrive an equation that only contains the variable y. So in equation 2, I'm going to solve for y, we have 3 fourth x minus y is equals to 4. Then my x in terms of y is 40 minus 3y over 2, so I'm going to substitute that one. 3 4 times 40 minus 3y all over 2, then minus y is equal to 4. Then I will going to multiply both sides by 4 so that the fraction will be removed. So 4 times 3 4, that will give me 3 times 40 minus 3y over 2, then minus 4y is equals to 16. Now I still have 2 in the denominator of my first term, so I'm going to multiply again both sides of the equation by 2. So I have 2 times 3 divided by 2, I only have 3. Then 40 minus 3y minus 8y is equal to 32. Then I'm going to distribute this, so I have 120 minus 9y minus 8y is equals to 32. I will combine these two like terms, negative 9y and minus 8y. That will give me negative 17y is equal to 32. Then we'll combine like terms, so 120 minus 32 is equals to 17y. Divide both sides by 17. Now my value of my y is 120 minus 32 divided by 17. That will give me y is equal to 88 over 17, or in decimal that is approximately equal to 5.176. Now to solve for x, I will going to use the value of y, and I'm going to substitute this to either equation 1 or equation 2, or this equation right here, wherein I already have an explicit equation for x in terms of y. So solving for x, I have the equation x is equals to 40 minus 3y over 2. So this one is much easier since this equation is already in uh, in an explicit form of x in terms of y. So 40 minus 3 times 88 over 17 divided by 2. So the numerator becomes 40 times 3, 40 minus 3 times 88 over 17. That will give you 416 over 17 divided by 2. Now 416 divided by 2, that's 208. So we have 208 over 17, or that is approximately equal to, in decimal, that's 12.235, approximately equal to 12.235. Now therefore, in ordered pair, the solution of this system of linear equation is 208 over 15 for x and 88 over 17 for y. Actually, we can see this solution if we're going to plot these two linear equations on the Cartesian coordinate plane. The intersection of these two linear equations is the solution of these two linear equations. So this is the graph of our two linear equations. The red one shows the first equation, and then the blue one shows the second equation. Now the point of intersection is right here, whose coordinates are 12.235 for x and 5.176 for y, and that corresponds to the value that we have just solved. So therefore, our answer is correct. Now if you don't have any graphing software, you can still check your answer by substituting the value of x and y to either of these two given linear equations. If it satisfies, then your answer is correct. Now let's proceed to the second example. We have 2x plus y minus 7 is equals to 0, and 6x plus 3y minus 11 is equals to 0. I will choose equation 1 for my first step. So in equation 1, I will going to get an expression for x in terms of y. So 2x plus y minus 7 is equals to 0. So I have 2x is equals to 7 minus y divided by 2. So I have x is equal to 7 minus y over 2. So I have just expressed x in terms of y using equation 1. Then I will going to substitute this expression to the variable x in the second equation so that I can come up with an equation that only contains one variable, and that is y. So in equation 2, I will going to solve for y once I substitute the expression for x. So equation 2, 6x plus 3y minus 11 is equals to 0. So substituting the expression for x in terms of y from equation 1, so 6 times 7 minus y over 2 plus 3y. I can also transpose negative 11 on the right side, so that is equal to 11. Then to remove the fraction, I will going to multiply both sides by 2. So I have 2 times 6 over 2, 7y, so it will become 6 times 7 minus y plus 6y is equals to 22. Then distribute 6 to each of the terms inside the parentheses. So 6 times 7 is 42 minus 6y plus 6y is equals to this is 132. Okay, 132. So I have 42 minus 6y, negative 6y plus 6y, that is equal to negative 0y, then equal to 132. Now transposing this on the other side as well as this one, so I have 42 minus 132 is equals to 0y, then divide by 0. Now we have a division by 0 here. Now if a real number is divided by 0, that will make the expression undefined. So therefore y here is undefined, or in other words, there is no real number that will satisfy our given equation. So you can have your answer in statement form that there is no real solution. Now we can also see this by graphing these two equations on the Cartesian plane. So this these are our linear equations shown in red and in blue. And by inspection, these two lines are parallel to each other. So therefore, there is no point of intersection between these two lines. So no real solution. Now let's proceed to the third example wherein we have a linear equation for our equation 2 and a nonlinear equation for our equation 1. Now equation 1 is nonlinear, it's because the degree here is 2. So this is a quadratic equation for y as a function of x. So again, the method of substitution can still be applied even if we have a nonlinear equation, as long as we have two available equations. Now for my solution, I will select the first equation, but this time um, I will going to express y in terms of x, because if I'm going to follow the same process from the previous example, I will end up with an equation that contains radical expression. So I will not allow that to happen within my solution. So this time I will solve for y in terms of x. So in equation 1, I'm going to express y in terms of x. So I have x squared minus y is equals to 0. Transposing negative y to the right side, so I have x squared is equals to y. Now I'm going to substitute the expression of y in terms of x to the second equation. So in equation 2, I'm going to solve for x. So I have 2x plus y is equals to 0. So 2x plus our y is x squared, so plus x squared is equals to 0. Then solve for x. So the common factor between the two terms is x. So I have x times 2 plus x is equals to 0. Now the next step is to equate both factors to 0. So we have x sub 1 is equal to 0. Then we have 2 plus x is equal to 0. So I have x sub 2 is equal to negative 2. So in this example, we have two values for our x. So in, it is also understood that we will also have two values for our y. So solving for y. For x sub 1 equals 0, we have y1 is equals to x sub 1 squared, so that's 0 squared is equal to 0. Then for x sub 2 is equal to negative 2, we have y2 is equals to x sub 2 squared, that is negative 2 squared. We have positive 4. So in ordered pair, we have two ordered pairs as our solution. Wherein the first pair has coordinates or has set of values 0 for x1 and 0 for y1. And for the second ordered pair, we have negative 2 for x and positive 4 for y. So this is the solution of our system of nonlinear equation, 0, 0 and negative 2, 4. If we plot these two equations, starting with equation 1, so our equation 1 is a parabola as shown in this red curve, and then our second equation is a line as shown by this blue line. Now we have 2 points of intersection here. This is our first point of intersection with coordinates negative 2, 4, and this one also corresponds to the values that we have just solved, so negative 2, 4. And then the second point or the second intersection is at the origin with coordinates 0, 0. And this is also the value that we have just solved right here, 0, 0. So therefore, these two ordered pairs satisfy our given system of linear equation. So therefore, we have a correct solution. Now let's proceed to the second method, the method of elimination. For this method, your goal is to make either one of the terms that contains the variable, make their coefficient equal only by its magnitude, and it's okay if they differ with the sign. Let's say for example, if we have 3x plus y is equals to 2, then right there we have negative 3x plus 5y is equals to 0. So for the term that contains x in both equation 1 and 2, they have the same magnitude of their coefficient, that's 3. They only differ with the sign. If that is the case, since this method is named as the method of elimination, we're going to eliminate, or in order to eliminate the term that contains x, we're going to add this to equation. By adding this to equation, the term that contains x will become 0, leaving only the term that contains y. So the resulting equation is a single equation with only one unknown. And with that, you can solve directly for y. And once you solve for y, substitute that value to either of these two equations to solve for x. So that is how this method works. So this is the procedure of this second method. So number one, if the given system of equations does not have the same magnitude of their coefficients either for x and y, what you need to do is try to find a number that if you're going to multiply this to one of the equation, it will result to a an equation whose coefficient for either x and y is the same in magnitude compared to the other equation. So that's the first step. Now, once you come up with that condition, the second step, just like this one, now we have 3x and negative 3x. Once you have this, after you multiply some number, the second step is to add the equations to eliminate one variable and then solve the resulting equation. Now, once you solve for the other variable, that is variable y, after you eliminate x, next is use the value for y and substitute this back to the two given original equations, either equation 1 or equation 2, to solve for x. And after that, don't forget the last step, you should check your solution whether it satisfies the uh, original equations or not. Okay, let's have our example for the second method. We have x plus 3 over 4, then plus y minus 3 over 3, y minus 1 over 3 is equals to 1, and 2x minus y is equals to 12. We have two equations whose degree is equal to 1. So we have system of linear equations. For my solution, I will transform first equation 1 into a simple equation without any fractions involved, or without or with only one term for the constant. So modifying equation 1, so x plus 3 over 4 plus y minus 1 over 3 is equal to 1. To remove fraction, I will going to multiply both sides by the LCD of 4 and 3, that's 12. So 12 multiplied by the first term, it will become 3 times x plus 3. Then for the second term, I have 4 times y minus 1, because 12 divided by 3 is 4. Then 12 times 1 is 12. Next is to distribute the numerical value to each of the term inside these two parentheses. We have 3x plus 9 plus 4y minus 4 is equals to 12. Then combine like terms. So 3x plus 4y is equal to combine the constant to the right side of our equation. So 12 plus 4 minus 9. We have 3x plus 4y is equal to 12 minus 4 plus 9. I don't know. 12 plus 4 minus 9. That will give you 7. So this is now the modified form of our equation 1. So equation 1, 3x plus 4y is equal to 7. Equation 2 is 2x minus y is equals to 12. By inspection, it would be easier to eliminate y if we're going to multiply 4 to all the terms in equation 2. In that way, the y term for the two equations will now have the same magnitude, and they only differ with the sign. So the next step is to multiply 4 to equation 2, so that the system linear equation becomes, so copy equation 1, it will become 8x minus 4y is equals to 48. So in this form, we found out that the y term for both equations have the same magnitude of their coefficient, that's 4, and then they only differ with the sign. Now we're going to eliminate y here by adding the two equations. So we have 8 plus 3, that's 11x. Then this one, we have 4y minus 4y, this is plus 0. is equal to this one. We have 12, I don't know, 48 plus 7, that will give us 55. The next, divide both sides by 11 to solve for x. So our x is equal to 5. So this is the value of our x. Now, to solve for y, substitute the value of x to either of these two equations. So solve for y using equation, actually we can use equation 2, and x is equal to 5. So we have 2x minus y is equals to 12. So transpose this to become 2x minus 12 is equals to y. Then substitute the value of x, that's 2 times 5 minus 12 is equal to y. So this is 10 minus 12 is equals to y. By symmetry, y is equal to negative 2. So in ordered pair, we have the solution of our system of linear equation with values 5 for x and negative 2 for y. If we plot these two equations, we will see that the point of intersection has coordinates 5 and negative 2. So that's correct. Now our blue line here corresponds to the second equation, and our green line, no, no, no. Our green line, by the way, corresponds to our second equation. Then our blue line corresponds to our first equation. Okay, so our solution here, or the values of our x and y, is correct. Now let's proceed to the last method. This is Cramer's rule in solving systems of linear equations. For Cramer's rule, we will use the concepts from matrix. So this is another method of finding the solution of a system of linear equations. So Cramer's rule uses the principle of determinant of a matrix. So later I will show you how to solve for the determinant of a matrix. But before that, we will discuss the procedure in performing this method. So first, you're going to convert the given system of linear equations with n unknowns into an augmented matrix. So an augmented matrix is of this form. So here on the left side, we have a system of linear equations. So these are linear equations because the degree is equal to 1. Now, you need to take note with the coefficients for x, y, z, as well as the constant, this one. Now, the coefficients as well as the constant will serve as your entries for generating the augmented matrix. Now, on the right, this one is your augmented matrix. To generate this matrix, you need the rows and the columns. Okay, this is these are our rows: row 1, row 2, row 3, and these are our columns: column 1 for x, column 2 for y, column 3 for z, and column 4 for the constant. So for column 1, you're going to list all the coefficients of the term x from equation 1 until equation 3, because this is 3 equations with 3 unknowns. So Cramer's rule can be applied. Now, um, you cannot only use Cramer's rule if the equal number of equations does not match with the number of unknowns. Okay, let's go back to the augmented matrix. So the second column corresponds to the coefficient of the y terms from equation 1 up to equation 3. Then for the third column, this one corresponds to the coefficient of the z term from equation 1 to equation 3. And lastly, for the constant column, so the constant column, by the way, is separated by these hidden lines so that we can see the coefficients and the constant that are separated by each other. So the constant, we have dh to l. Now once you have this augmented matrix, this will serve as your guide when generating the other matrices that are needed for this method. So let's start by generating the matrix for the x variable. Now, for each of the matrix that we're going to generate here, starting from x, the size of this matrix is 3 by 3. What does it mean for a 3 by 3 matrix? So this matrix consists of 3 rows, row 1, row 2, row 3, with 3 columns. So column 1, column 2, and column 3. Now, in generating this matrix, it is so arranged such that the the entries for the x column will be replaced by the constant because we are aftering with the matrix for the x variable. Then the remaining two columns are for the coefficients of y and z. So since we are going to generate the x variable here, so replace the entries under the x column with the entries under the constant column. So we have here the DHL. So that is how you generate the matrix for x variable. Now the next step is generating the matrix for y variable. So same pattern with x, since we are after with the generation of the y the matrix for y variable. Now we're going to replace the second column with the entries under the constant column. So we have DHL. Then the first column will be for x, then the last will be for z. And then the next one is for the z variable. Now this time you're going to replace the third column with the constant column. Then the first for x and then the second for y. And finally, if you're going to generate the last matrix that is for the constant, all the columns contain the coefficients for x, y, and z. So these columns cannot be interchanged. So it must start with the first column that is for the coefficient of x, second column for y, and then third column for the third third variable that comes or that appears on the given system linear equation. So it is not allowed to interchange these elements. So x for x, y for y on the second column, and then z for z on the second column. And once you generate these matrices, the next step is to solve for the determinant. Solve for the determinant of the matrices x, y, z, and the constant, and then apply the formula below. So to solve for the value of x, simply divide the determinant of x by the determinant of the constant matrix. Then for y, that's the determinant of y over the constant, and then for z, that's the determinant of z over the constant. Now the question is, how are we going to solve for the determinant in the first place? So I will show you the way on how to solve for the determinant, starting with 2 by 2 matrix. So for 2 by 2 matrix, this applies for two equations with two unknowns. Okay, so let's say we have our matrix A with elements A, B, C, D. So we have two rows and two columns. To find its determinants, so the the notation is that determinant of matrix A, that is equal to, so make some diagonals starting with a diagonal from top left to bottom right. You're going to multiply these two elements, so A times D, then minus, draw a diagonal that is opposite in direction from the first, so B times C. If the diagonal is in opposite direction, the operation here is subtraction, so minus B times C. So that's it. This is how you get or solve the determinant of a 2 by 2 matrix. So this one will apply for two equations with two unknowns. How about for 3 by 3 matrix? Now this will apply for three equations with three unknowns. Okay, so let's say we have matrix B with elements A, B, C, D, E, F, then G, H, I. Now we're going to use the basket method. Same with the first. We will create some diagonals. So start from a diagonal that is drawn from top left to bottom right. So A, E, I. So since we are now on a 3 by 3 matrix, so the number of products that appears here is 3. So A, E, I, then plus, make another diagonal, so BF. Now, since it lacks one entry, so multiply it to G, not to HD, because it will become four products, so only G. So we have BFG, then plus, here we have one entry, so we're going to multiply this to the remaining two entries. We have plus CHD. Then next, make a diagonal that is opposite in direction from the first diagonals that we have drawn. So we have C, E, G. This time the operation is subtraction, so minus C, E, G. Then minus, second one, B, D, I. So B, D, I. And lastly, we have A, H, F. So minus A, H, F. Then simplify. So this is how you solve for the determinant of a 3 by 3 matrix. For four equations with four unknowns, this method will not be applied anymore. So this is not applicable already for four equations, four unknowns, or higher number of equations with corresponding unknowns. Now there's another method for that, and it is out of scope of this video. Okay, let's have some example. We'll start with two equations with two unknowns. So expect that you can generate 2 by 2 matrix. So we have a given system linear equation, but we need to modify this one first because this is in general form. We want to rewrite this in such a way that all the constants should be on the right side. So we have 6x minus 3y is equals to 4, and x plus 2y is equals to 4. Now with this form, we can proceed to the creation of the augmented matrix. So for the augmented matrix, we only have two rows because we only have two equations. Then we have three columns. These are the coefficients for x, for y, and a constant. So for the first column, that is for the x, so that's 6, 1. Then for y, we have negative 3, 2. Then separate the coefficients from the constant using this hidden line. So we have 4 and 4. So this is for the constant column. Next, generate the matrices. So for matrix x, for the x variable, here replace the first column by the elements under the constant column. So that's 4, 4. Then for the second column, that is for y. So negative 3, 2. This one right here. So this is our matrix x. Next, generate the matrix for the y variable. So for y variable, replace the entries under the y column with the entries under constant column. So that's for the second column. For 4 instead of negative 3, 2. Then for the first column, that is for the x. So 6, 1. And lastly, for the constant matrix. For the constant matrix, simply copy the first and second column that appears from our augmented matrix. So 6, 1 and negative 3, 2. Okay, the next step is to determine the determinant of a matrix. So since this is a 2 by 2 matrix, we only have two terms for our determinant. So first term for the diagonal from top left to bottom right, so 4 times 2, then minus the opposite diagonal, we have negative 3 times 4, that will give us negative 12. Simplifying further, this is 8 plus 12, that will give us positive 20. So this is the determinant of our matrix X. Next, for Y, so multiply this, 6 times 4, then minus 4 times 1, 4 times 1. This is 24 minus 4, the result is 20. Then lastly, for the constant matrix, so 6 times 2, then minus negative 3 times 1, so that's negative 3. This is 12 plus 3. The determinant of the constant matrix is 15. Now the last step is to solve for x and y using the formula. To calculate x, simply take the ratio of the determinant of matrix x over the determinant of the constant matrix. That is equal to 20 over 15. That is equal to 4/3. Then for y, that's the determinant of matrix y over the determinant of the constant matrix. Okay, so for the determinant of y, that's 20. That's 20 over 15, or the lowest term is 4/3. So therefore, the solution of our system of linear equation is consist of only one ordered pair with values 4/3 for x and 4/3 for y. So we have the same values for both x and y. So to check this, your assignment is to substitute these values back to either of these two equations. If it satisfies, then this ordered pair or these values is indeed the solution of our given system of linear equation. So this is how you carry out Cramer's rule for two equations with two unknowns. Now let's try three equations with three unknowns. We have 2x plus 4y plus z equals 1, x minus 2y minus 3z is equals to 2, and x plus y minus z is equals to negative 1. Since the given system of linear equation is already of the form ax plus by is equals to the constant, wherein all the constant are already on the right side, then proceed directly to the creation of the augmented matrix. So for the augmented matrix, we have three rows because we're given with three equations, and we also have four columns. So the first column is for the coefficient of x, so 2 1 1. Second is for y, we have 4 negative 2 1, and then the third one is for z, we have 1 negative 3 and negative 1. Then the last column is for the constant, we have 1 2 negative 1. Next, generate the matrix for variable x. So for variable x, since this is a three unknown system of linear equations, expect that the size of your matrix is 3 by 3. So for the first column, since we are to generate the matrix for the x variable, replace that with the constant. So 1 2 negative 1. Okay, the entries under the constant column. Then for the second column, that is for y, then the third column is for z, so 1 negative 3 negative 1. Next, the matrix for variable y. So this time, replace all the entries under the second column and replace it with the entries under the constant column. So for the first column, that is for x, second is for the constant. So 1, 2, negative 1. The third column is for z. 1, negative 3, negative 1. Next, for matrix Z. For matrix Z, I replace all the entries under the third column with all the entries under the constant column. So we have 1, 2, negative 1. Then for the second, that is for y. So 4, negative 2, 1. Then the first is for x. 2, 1, 1. And lastly, for the constant matrix, we have all the entries for the coefficients of x, y, and z. So 2, 1, 1, 4, negative 2, 1, then 1, negative 3, negative 1. Next, we'll proceed to uh, the determination of the determinant. So for matrix X, we have 1 times negative 2 times negative 1, that will give us positive 2. Then plus 4 times negative 3 is negative 12 times negative 1, that's positive 12. Then plus 1 times 1 is 1 times 2 is 3, so positive 3. Then minus this one, 1 times negative 2 times negative 1, that's positive 2. Then 4 times 2 is 8 times negative 1, that's negative 8, so minus negative 8. Then lastly, 1 times 1 is 1 times negative 3 is negative 3, so minus negative 3. Simplifying this, we have 2 plus 12 plus 3 minus 2. Negative 1 times negative 8 is positive 8. Then negative 1 times negative 3, that's plus 3. So we have 2 plus 12 plus 3 minus 2 plus 8 plus 3. That will give us 26. Okay, now let's review. 1, 2, negative 1, 4, negative 2, 1, then 1, negative 3, negative 1. This is positive 2. This one is 4 times negative 3, that's negative 12 times 1, positive 12. Then 1 times 1. Okay, so here 1 times 1 is 1 times 2. It should be 2, not 3, right here. So this must be 2. So therefore the final answer is not 26, but rather 25. Okay, now let's proceed to matrix Y. So we have 2 times 2 is 4 times negative 1, that's negative 4. Then plus 1 times negative 3 is negative 3 times 1, that's negative 3. Then 1 times negative 1 is negative 1 times 1, that's negative 1, so plus negative 1. Then the opposite diagonal, 1 times 2 times 1, that's minus 2. 1 times 1 is 1 times negative 1, so that's minus negative 1. Then minus 2 times negative 1 is negative 2 times negative 3, so that's positive 6, so minus 6. Simplifying this, negative 4 minus 3 minus 1 minus 2 plus 1 minus 6. The result is negative 15. Now let's proceed to matrix Z. So for matrix Z, 2 times negative 2 times negative 1, that's positive 4, plus 4 times 2 is 8 times 1, that's 8. Then plus 1 times 1 times 1, that's 1. Then minus 1 times negative 2 times 1, that's negative 2. Then minus 4 times 1 is 4 times negative 1, that's negative 4. Then minus 2 times 1 is 2 times 2 is 4, so minus 4. Simplifying, 4 plus 8 plus 1 plus 2 plus 4 minus 4, that's 15. And lastly, for the constant, so 2 times negative 2 times negative 1, that's positive 4. Then plus 4 times negative 3 is negative 12 times 1, so we have plus negative 12. plus 1 times 1 times 1, that's plus 1, then minus 1 times negative 2 times 1, that's negative 2, minus 4 times 1 is 4 times negative 1, so minus negative 4, and then minus 2 times 1 times negative 3, that's minus negative 6. Simplifying, 4 minus 12 plus 1 plus 2 plus 4 plus 6, the answer is 5. So now that we have already solved for the determinant of each of the given matrix, next is to solve for the values of x, y, and z. So for x, that is equal to the determinant of x over the determinant of the constant. So we have 25 over 5. The answer is 5. For y, we have the determinant of y, that's negative 15 over the determinant of the constant, so that's negative 3. Then for z, we have 15 over 5, that is positive 3. So therefore, the solution of the system of linear equations is represented by the ordered pair whose x value is 5, y value is negative 3, and z value is positive 3. Now, your assignment here is to substitute each of these values for x, y, and z back to our original system of linear equations. So you can choose either equation 1, 2, or 3. Now, if it satisfies either of these three linear equations, then our solution right here is correct. Okay, so that's it for this video. I hope you learned something. Thank you and God bless.